while you're writing your questions, I'm just going to remind you where we are. So last week we did 1 through 7. You just took your quiz. I'll give those back in a couple of minutes. And I posted the solutions to that quest on Moodle, and I handed out hard copies as you left. So this will be there permanently throughout the semester. It will be really handy to refer to that or your own quest when you're studying for the final exam. Okay. So this week, you were meant to watch lectures 8 through 16 from the course video lectures playlist. The packet with notes for 8 through 16 was over here Thursday. I forgot to remind you. Many of you took it anyway, but it's here if you don't have it yet. So that's the week 2 packet, and there's no lecture 11 or 12, and there's no homework 11 or 12 in case you didn't notice that. So supposed to do the assignments in Wiley Plus, work on the activities in the packet, and then today we're going to answer as many questions as we can fit in an hour and a half. Thursday we'll have a quest on the 8 through 16 lecture material. All right. Okay, I'm going to start with the questions that are either a little bit more generic or just aren't in Wiley Plus. Okay. So we want to analyze the end behavior. Can everybody read that? Okay, good. End behavior of the function f of x equals x to the 5th minus e to the x. Okay, so basically we want to know what happens as x approaches infinity and what happens as x approaches negative infinity. So we'll do infinity first. Okay, so we have to think about what happens to x to the 5th when x gets really, really, really big. 10, 100, 1,000, 1,000,000, a quadrillion, and then you raise it to the 5th power. What's happening to those x values? They're just getting really, really big. Right, so as x goes to infinity, that goes to infinity. And what happens to e to the x as x gets really, really big? Also goes to infinity, yeah. So is infinity minus infinity 0? Yeah, not really, because some infinities are bigger than others. Yeah, I know that sounds crazy, but think about how many counting numbers are there? Like 1, 2, 3, 4, 5, et cetera, et cetera. How many? Infinite, infinite. How many even counting numbers are there? 2, 4, 6, 8. It's still infinite, but it seems like there's only half of the counting numbers, right? So what the notes this week talked about was the dominance of some functions over others and how fast they get big, right? And exponentials always beat power functions or polynomials. Okay, so e to the x is going to get bigger way faster than x to the 5th gets bigger. So x to the 5th is getting big, but you're subtracting something way bigger. So what do we think is going to happen here? So something big minus something much bigger. It's going to work its way towards negative infinity, I think. I think it's negative infinity. But if you have any doubt at all, we can look at a graph of this thing and try to find its end behavior that way. Okay, so I've got f of x equals x to the 5th minus e to the x. So just like in your graphing calculator, the little caret gives you the exponent in GeoGebra. So x to the 5th minus e to the x, and we graph it. And then we can play with the scale so we can see what happens as x goes to negative infinity. So it looks like I don't even have to go that far in the x direction. And I can see that this thing is going down to negative infinity. So as x goes far to the right, as my x's get bigger, the y values of this function are getting really, really small, going down towards negative infinity. Okay, so we are doing infinity minus infinity, but the answer is negative infinity, which feels crazy, right? But you have to think about the which function is going to dominate. The one e to the x gets bigger faster, so you have something big, but minus something really, really big, and it's going to end up going to negative infinity. All right, let's think about the behavior at the other end. The limit as x approaches negative infinity. So what happens to this function as the x values become really, really negative? Negative 10, negative 100, negative 1,000, negative 1,000,000. All right, what happens to x to the fifth? Goes to negative infinity. Right, because x to the fifth looks like something like this. And when you raise something to an odd power, you raise a negative to an odd power, it just comes out negative again. So it'll be really big but negative value. All right, and then e to the x, what happens as x becomes really negative? Very small. Yeah, think about the graph of e to the x. It looks like this. Right, so as x goes to negative infinity, the y values of e to the x are getting really small or really close to 0. Right, so this thing is going to 0. So negative infinity minus 0 is negative infinity. So its end behavior in both directions is negative infinity. So this analyzing the end behavior of functions, really important concept heading into calculus. Being able to think about what happens to the value of an expression as the x values get really big or really small. If I understand and can do problems in the packet, will I pass the quest? Or what are the concepts that we are working on? Okay, so probably I would also do the homework. But yeah, if you understand the stuff in the packet and can do all the problems in there, yeah, you'll probably pass the quest. The concepts that we're working on this week, why don't you guys tell me, what did you learn about this week? Yes, log scales. Those are kind of cool. What else?
We went a little more in depth with inverse functions.
Yep, inverse functions was an important concept. Yeah, we did a little bit of intro to trig, sine and cosine. With right triangles, radians, and the unit circle. Right. Unit circle, yeah. Polynomials, yep. Power and polynomial functions. What about them? Yeah. So it's pretty much a review of the same things. Like if I give you some information about the function, can you write a formula? If I give you a formula, can you draw me a graph? So basically, we need to be able to go from data to formula to graph, right? From a table of values, you need to be able to take that to a formula or a graph and sort of do this from any direction. And we did that with logarithmic functions too. A little bit of log and exponential functions seeped into this week also. And then going along with inverse functions was composing functions, where you plug one function into another. End behavior, like the problem we just talked about. What else? There's one more biggie that I can think of. Limits, that's end behavior, yeah. But we actually did a little bit of limits that wasn't end behavior, where we approached a number. Yeah. We did some regression. Yeah, I actually forgot about that one. We did some linear regression and some regression where you took the log of one of the data points. One more. Close. Rational functions. Right, like the horizontal asymptotes and the vertical asymptotes and the zeros and all that. So I think that that's pretty much all the big ones for this week. So some of it's review, right? Some of it's brand new. But yeah, if you can do the stuff in the packet, you should be pretty well set for the test, but definitely also do the homework. If you do both of those things, you will definitely be all set. Okay, can you do another example of an inverse function? The steps helped a lot, but I'd like to see another one done out. Sure, okay, so let's say I have a function f of x, which equals x plus 1 over x minus 1. This gives us a chance to look at a rational function, and I would like to find its inverse. Okay, so basically an inverse changes the role of input and output. So the way it's written now, x is the input, y is the output. I'm going to reverse it so that the outputs become inputs and the inputs become outputs. So many people will tell you, first of all, replace the f of x with a y, right? F of x is just a fancy name for y, and this just makes the algebra look a little nicer. All right, so you could just solve this for x and then change the x's to y's and y's to x's, or you can do the change first and solve for y. It's the same thing. So if I make all my y's x's and all my x's y's, then I want to solve for y. So the reason we make this switch is because that's what an inverse function does. It reverses the role of input and output. So the y's are outputs, they become inputs, and the x was an input and it becomes the output. So you switch the x's and y's. Then you just have to solve for the y. Okay, so the whole idea here now is I just need to get the y by itself. So I'm going to multiply both sides of this equation by my y minus 1. So on the right, they cancel. And I have y plus 1 equals xy minus x. Okay, so if I want to solve for y, I should put all the y terms together on one side of the equation. So and all the non-y terms on the other side. So I'll add x to both sides. So I have x plus 1 equals xy minus y. All right, now what? Trying to get that y by itself. What do I do?
Factor out the y.
Factor out a y from the left side. Common term, yeah. So we have a y. And if I reverse distribute one of the y's, I'm left with an x minus 1 equals x plus 1. And then to get the y by itself, divide by that coefficient on y. Divide both sides by x minus 1. So I get y equals x plus 1 over x minus 1. That's my inverse function. Yeah, let's, ooh, look at that. So f inverse of x is x plus 1 over x minus 1. Yeah, so this is an interesting function because it is its own inverse, right? What do you know about the graphs of inverse functions? Symmetric about the line y equals x. So let's look at this graph of f of x. All right, if I graph the line y equals x, if I were to reflect this graph, the f of x, about the line y equals x, it lands right on top of itself. So that's why it is its own inverse. Is there a way to tell if I've skipped any problems or gotten any wrong from the assignment page without waiting till they're late? Yes, pretty sure. So when you're in the Wiley Plus, so I'm in the assignment page, but if I click on my grade book over here, instead of looking at the assignment page, go to grade book. And wait and wait and wait and wait. There we go. It gives you your score on all of the assignments. So these are my scores, which are pretty terrible because sometimes if I know how to do it, I just click through and sometimes I do the whole thing. I get a 10 out of 10. Right? So if it's red, that means it's been marked late. You didn't do it in time. And let's see, if I look at this 10 out of 19, it's on homework 14. I'll click homework 14. And it tells you your score on each problem. So you can go in and find the particular problems that you got wrong or didn't do. So from the grade book, you can find those things. So homework 9, number 7. I know that the graphing part was a pain, the part at the end. But like, I'll show you what my graphs looked like. Because if that was the part that bothered you, yeah, if that was the awful part. So see, I was trying to graph the point 821, right? I zoomed in as far as I could, and I couldn't get it to do it. And I finally did 821.7, and I was like, close enough, right? And then I was supposed to do 17,195, and the best I could do was 17,184.8, right? So I just got as close as I could and clicked submit, and it took them, right? So the tolerance must have been pretty high on those. Yeah. The line, so my line was y equals 228x minus 3,434. So yeah, I just used the y-intercept and the x-intercept, and I got as close as I could on the x-intercept, and it took it. It's 15.1 or something. It didn't work for you? Yeah, I don't know. Don't let this get to you. I'll go through and give everybody credit for these graphs if they look all right. So, but people actually So two people asked for this question. Do we actually need to do it, or was it just the graph thing that was annoying? What? Just the graph? Okay. All right. I thought it was kind of cool, though, this whole log regression thing. But, okay. All right, so then let's look at part B of number 5. Okay, using the results of part A, plot the integer points 2 through 9 and the multiples of 10 from 20 to 90 on the log scaled axis. So basically, in a log scaled axis, instead of, if we want to plot the points 2 through 9 and 0 to 20, sorry, 2 through 9 and 20 to 90, I'm plotting the power of 10 that each number is, right? So instead of plotting the number 2 is 10 to the 0.3010, right? So if I type into my calculator, so what we did is we took the log of each number. So if I take the log of 2, I get 0.3010, blah, blah, blah. And that's what you put into your little table. That means that 2 to the 0.3010 should give me, oh, sorry, 10 to the, yeah, 10 to the 0.3010 should give me close to 2. It's not giving me exactly 2 because I rounded that 0.3010. Right, okay, so that means that instead of plotting the number 2, we're plotting it as 10 to the something. And the something, the exponent, is 0.3010. So we're doing 10 to the 0.3010, which means that I can't start my number line at 10 to the first because 10 to the 0.3 would be to the left of that. So it has to be the number line that starts at 10 to the 0, and there's only one of those. And then between 10 to the 0 and 10 to the first, right about here, would be 10 to the 0.3, right about a third of the way between 10 to the 0 and 10 to the first. Right? And then 3 is really 10 to the 0.4771, right? Almost halfway between 10 to the 0 and 10 to the first. So that 3 is about halfway between 10 to the 0 and 10 to the first. That's how you plot on a log scale. Okay, we'll start here. This is from the class 10 activity. All right, we're supposed to find the inverse of this function, p inverse of x. So start by replacing p of x with y. Change all the y's to x's and all the x's to y's. And then I want to solve this thing for y. I have to try to get y by itself. So I'm going to multiply both sides by e to the y plus 5. So over here they cancel. And over here I have x e to the y plus 5x equals e to the y plus 2. So I should try to gather all the terms that have y's in them on one side. All the terms that have a y will gather together. All the terms that don't have a y will push off to the other side. So this is going to be 2 minus 5x. Move the 5x over. And this is x e to the 5y minus e to the y. I'm sorry, what did you guys say? Oh, sorry, it's just to the y. That's good, that makes it easier to solve. Okay, so now, just like in the last example I did with finding an inverse, we have a common term, e to the y, in both of these terms here. So we have e to the y. Reverse distribute that, and we have times x minus 1 equals 2 minus 5x. Okay. So then to get e to the y by itself, divide both sides by the x minus 1. So we have e to the y equals 2 minus 5x over x minus 1. And then how do I get the y all by itself? Logarithm. Yeah, take the natural log of e to the y, because the natural log of e to anything is that anything, right? Because natural log and e to the something are inverse functions and they undo each other. So I take the ln of both sides. So this just becomes y is equal to the natural log of 2 minus 5x over x minus 1. You could play around with some properties of logarithms here if you wanted to, but I'm going to say that's good enough. Does that make sense? Okay. If it was not invertible, that's, you could just say this function has no inverse. What would that look like? Okay, so you would check, you're right, I should have checked first. I would look at its graph and see if it passes what? The horizontal line test, yeah. Mm-hmm. Okay, that's a fundamental misunderstanding. Okay, so it's not a misunderstanding. It's the way we have defined the square root function. So if the square root of 4 were defined as plus or minus 2, you're right. The square root function would, the square root would not be a function, right? Because 1 input, 2 outputs, that means not a function, right? It wouldn't pass the horizontal line test. If when I was graphing this thing, when I put in a 4, I got a positive 2 and a negative 2. It would look like a sideways parabola, right? However, the square root of 4 does not equal plus or minus 2. It's not true. The square root of 4 is 2. And this is how mathematicians have defined the square root. They said the square root is the positive number that when you square it, you get the 4 back. Right? This is the definition of the square root. If you want plus or minus, you have to put a plus or minus in front of the square root. Right? So when we solve, say, x squared equals 4, we say, okay, that means x is plus or minus the square root of 4. We have to add the plus or minus. You can't just write square root of 4. The plus or minus has to be in front of the square root in order to include both. It's just how it's defined, yeah. I know, me too. Even the first year I was a teacher and I taught high school, I told my students the square root wasn't a function, and I was wrong. Yeah. So the square root thing, the square root of x squared, the definition of this thing is actually the absolute value of x. Right? So the square root of 4 is actually the absolute value of 2. And that means that this thing this x could be positive or negative, right? Because the absolute value will always give you the positive. That's a good question. Thank you. Yeah, because another way to think of this is the graph of x squared looks like this, right? And you say, well, x squared doesn't pass the horizontal line test, which means it should not have an inverse. So mathematicians just said, well, yeah, technically, right? But we can fix that. if we just ignore this piece, right? We'll just look at f of x equals x squared only for x is bigger than or equal to 0. So we restrict the domain. So if you ignore the left half of this thing, now it passes the horizontal line test. And its inverse looks like that, which is the positive square root of x, because we restricted the domain of this thing to be positive. No, the trig functions also don't have an inverse, because you learned what the trig functions look like, right? I think. Just a wave, right? That thing would not pass the horizontal line test. But we do a similar thing where we say, well, it would pass if we only looked from, say, here to here, right? If you just looked at this piece of the wave, that passes. So we'll create an inverse just on that piece. We'll talk about that later. Okay, here's a function, a quadratic function, negative 4.9 t squared plus 19.6 t. It's defining the domain as t's only go from 0 to 4. And it tells you the height of a ball in meters, t seconds after it was thrown upward with an initial velocity of 19.6 meters per second. Okay, so the restriction on the domain makes a lot of sense given the context of this problem, because before time equals 0, we don't know what the heck that ball was doing. It was like in somebody's pocket or desk drawer or something. So this function does not model at all what that ball was doing before we threw it. And at 4 seconds, what do you think happens to the ball at 4 seconds? Probably hits the ground, yeah. So this function is no longer going to model what it does after 4 seconds, because after 4 seconds, this thing would predict that it like falls through the earth, right? So we have to restrict the domain to 0 to 4 seconds. All right, why do you think f is not invertible? Right, it's an upside down parabola because the ball goes up and comes down. So each height that it hits that height twice. So it's not a one-to-one function. So it's not one-to-one. In other words, it doesn't pass the horizontal line test. All right, so now we want to restrict the domain, similar to what we were just talking about, restrict the domain so that it is invertible, and then find a formula. Okay, so I need to take a look at this graph so that I can accurately restrict the domain. Negative 4.9 x squared plus 19.6 x, was that it? I think, let's double check. Yeah. All right, and that's 0 to 4, so I'm just gonna move my window a little bit. Okay, so if I chop off, if I just get rid of part of this graph, I'm going to arbitrarily choose which half to get rid of. I just have to pick part of it so that once I get rid of it, the rest of it passes the horizontal line test. So right here is about the halfway point. It looks like it's at 2 seconds. And then I'll just get rid of the stuff over here. You could have just as easily chosen to get rid of the left half. Doesn't matter. You just have to get rid of any half you want so that the remaining part passes the horizontal line test. So I'm going to restrict my domain to 0 to 2. So I'm going to restrict my domain to 0 to 2 seconds instead of 0 to 4 seconds so that it passes the HLT. And then to find the inverse function, replace f of t with a y. Replace all the y's with t's and all the t's with y's. And then I have to solve for y. Okay, so I'm going to move the t over, and I get 0 equals negative 4.9 y squared. And use the quadratic formula, right? So y is going to be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And then you can simplify that by yourself, but that's the inverse function. So to use the quadratic formula, it has to equal 0. One side has to equal 0. So I moved the t over so that I would have a 0. And that t becomes the constant, right? That's my value that has no y attached to it. So that's like my c in the quadratic formula. So that'll be that. You might do a little arithmetic under the radical to make it look prettier, but that's basically it. Okay, interpret the function f inverse. What are its units for input and output, and what does it represent? Okay, so the input for the original function f was time, and the output was h. Inverse functions reverse that. So my input is going to be height in feet. So think of it as like a computer where you type in the height in feet, press enter, and out pops what time it was that the ball hit that height. So my output is time in seconds. And it'll just be between 0 and 2 seconds. The output will always be between 0 and 2 seconds. Because that's how we restricted the domain of the original function. Good question. When the variables represent real things, I shouldn't have switched them like I did. So first of all, this is supposed to be t is restricted from 0 to 2, not x. And here, I should not have swapped my y's and my t's. I should have just solved for t, because t always represents time. When my input is supposed to be height and my output is supposed to be time, so this should have stayed a t, and this should have stayed a y. So that your input is height y, and your output is time t. So this should have stayed y, this should have stayed t's. And then just solve for t. Yeah, so this is one of the things that I find particularly confusing about inverse functions, is that when you're just dealing in abstract x's and y's, we typically call x the input and y the output. So when we find an inverse function, we just rename the thing that used to be the output y, we rename it x because now it's an input to a different function. But when they represent real things, you can't just rename time height and height time. Like, that is like crazy, right? So you don't switch the variable names in a real life situation like this. Sure, you could. If you're in the habit of switching it, that would be fine. Yeah. Switch it and then switch it back. Okay. 11.1, question 39. The circulation time of a mammal, the average time it takes for all the blood to circulate once and return to the heart, is governed by the equation T equals 17.4 m to the 1/4. So m is the body mass of the mammal, and T is the circulation time in seconds. So we want to fill out this table where we have some masses of different animals and we want to put in the circulation times. So quick way to do this using a graphing calculator is to put the function in y equals. You could also do something like this in a spreadsheet or in GeoGebra's spreadsheet, x to the 1/4. So you just type the function in y1 and then use your table feature, which is the second graph function, and then we can just type in all the x values we want, and it'll tell us the y values. So I'm going to put in 5,450, 2520, 70. What else do I want? Oh, that's it. Okay, cool. So these would be 149.5, 123.28, and 50.33. So we're just plugging in numbers into the function that they gave us. And then for part B, if the circulation time is 2.3 times that of another, what is the relationship between their body masses? Okay, so let's let, I don't know, Z be the slower circulation time. Sorry. Let's not say slower or faster, let's say shorter. Okay. So then the longer circulation time would be 2.3 times Z, right? All right, so what is the relationship between their body mass? So the formula is that time is 17.4 m to the 1/4. Okay, so if one of these things is Z, right? One mammal has circulation time Z. And the other mammal has circulation time 2.3 Z. What I need to do is solve each of these equations for M and compare the masses of the two different animals. So solve each one for M in terms of Z. So I'm going to divide by 17.4. Z was a terrible letter choice since I have 7s and 2s in here. M to the 1/4. And then how do you undo M to the 1/4? How would you get that as a plain old M to the first? Raise it to the 4th power. Yeah. So when you raise a power to a power, you multiply the exponents, and 1/4 times 4 would give me M to the 1st. So I'm going to multiply both sides, raise both sides to the 4th power. So I have Z to the 4th over 17.4 to the 4th, whatever that is, equals M. Similar problem I do over here. So I'm going to have 2.3 Z over 17.4, all raised to the 4th to give me M. And then when I simplify this thing, I have to raise the 2.3 and the Z to the 4th power. So I get 27.9841 Z to the 4th over 17.4 to the 4th. All right, so for both of these, I solved for M in terms of Z. And these two expressions are almost exactly the same, except for this coefficient on the Z to the 4th. Right? For the Mammal with the longer circulation time, its mass is bigger by a factor of 27.9841. Right? The coefficient over here is just a 1. And over here it's a 27.98. So it's bigger by a factor of 27.98. Is approximately 28 times the body mass of the other animal, if you round to the nearest whole number. That make sense? Good. I like that you guys nod at me. Okay, so the unit circle. It is a circle with radius 1, that's why we call it the unit circle, that's centered at the origin 0, 0. So we always measure angles in the unit circle just as a matter of convention, not because it's like more correct than any other way, but it's just a matter of convention so that we all do it the same way. We always measure angles starting from the positive x-axis. This is your starting point, 0 degrees, and then we go counterclockwise. So if I want 130 degrees, I would start here at the positive x-axis. Right? That gets me to 90. If I continue going, that's 180, right? So it's somewhere between 90 and 180. Halfway between would be 135, so almost halfway. So this angle is about 130 degrees. And then they may have wanted you to mark it with a point as opposed to drawing an angle, which could be confusing. So if you were going to mark this with a point, you would put it like somewhere here-ish. It has to be exact to figure out what the point goes. Okay, so the coordinates of this point, right, should be cosine of 130 comma sine of 130. And then you would just use a calculator to get those as a decimal. Because that's the definition of the sine and the cosine. In the unit circle, the cosine is the x coordinate where the angle intersects the circle, and the sine of the angle is the y coordinate where the angle intersects the circle. So we just got to make sure you're in degree mode. So if you hadn't heard of radians before you did this problem, you had to know that there's another way to measure angles and put this in degree mode. And then cosine of 130 is negative 0.6427, and the sine of 130 okay, so let's call that back up and put it on there. Negative 0.64. So I got to go left, right a little bit. Okay. And then 0.766. There we go. So that should give me a partially correct. No. Oh, maybe it doesn't, just has to mark the whole thing right or wrong. Okay. Oh, cool. Thanks. So once you click into the graph, if this point were in the wrong place, it would have a little red mark to tell you it was wrong. Good to know. All right, so let's just do one more. So the 130 was pretty easy. Let's do a -1, like negative 190. So negative 190, we always start in the positive x-axis as my 0 degrees. And we move counterclockwise for positive angles and clockwise for negative angles. So I want to go 190 degrees, but in the clockwise direction. So we've got 90, 180, 190 is a little after that. So my final would be right here. And then the coordinates of that point would be cosine negative 190, sine negative 190. You could also put in cosine of positive 170, because if you start at the positive x-axis and go 170 degrees in the counterclockwise direction, you'd land at the exact same point. Yeah. So you can do either one. Your calculator will be able to give both of those angles to you. Mm-hmm. Huh. Okay. Which one is 130 the same as? Maybe 1,000, because it's not 210, and we just did negative 190. Negative 485 is like here. And 1080, I think, is a multiple of 360. So it's got to be the 1,000. So let's see, 1,000 minus 360 minus 360, because you can keep subtracting 360 and you'll land in the same exact place. You can always add 362. So 280, yeah, it's not the same as 130. I might have had different numbers than you. Yeah. All right, so sure. The equation of a circle is x minus h squared plus y minus k squared equals r squared in general, and the well, this is sort of this, I think this is the simplest way to write the equation of a circle. Its center is at hk and its radius is r. So for the unit circle, its equation would be x squared plus y squared equals 1. So if you wanted to solve it for y, because that's how we're used to looking at functions, it would be y equals plus or minus the square root of 1 minus x squared, which is really two different equations. Because a circle is not a function, right? So you have to have a positive square root and then another equation for the negative square root. So if you wanted to use your graphing calculator, you'd have to put in two different equations. Here's one place where GeoGebra has an advantage over the graphing calculator, is that it will graph implicit functions. Go away. So I can graph x squared plus y squared equals 1. And it looks funny because this is an unsquare axis. There we go. So you can just type in, this is called an implicit function, an implicit equation when it's not written in the form y equals. Yeah. Okay, so I think that finishes up that problem. That's my list of blue slips. Anybody else have anything else? So this is homework 14, second to last question. Okay, so the definition of a power function is y equals a times x to the b. Right? So like 3x squared would be a power function, where a and b are constants. Right? X is the only variable. So we'll mark the variable in a different color here. X is the only variable, A and B are constants. And the definition of exponential looks like y equals a times b to the x. Again, a and b have to be constants. So the only variable is in the exponent. So x to the x, it kind of looks like a hybrid of a power function and an exponential function because it has a variable in the base, like a power function, and it has a variable in the exponent, like an exponential function. But it doesn't meet the definition of either kind of function, right? Because for a power function, the exponent must be a constant. And for an exponential function, the base must be a constant. So because the base is a variable here, it can't be exponential. And because the exponent is a variable, it can't be a power function. It's just because of the definition. Yeah. Okay. For x to the x. It's an interesting function. Let's look at its graph. So what do you think? Does it have an inverse function? No, it doesn't pass the horizontal line test. And something else might happen when we go far out in x, because this thing's going to get huge really fast. It just gets big really fast, and it does not have an inverse, because when we zoom in on the beginning, it definitely has a dip. Interesting function.